So let's get started talking about Kokkos and similar approaches for performance portability. So the overview of the talk is here. We're going to talk about the concept of performance portability and some of the patterns and for doing this, and then some Kokkos specifics about how it controls your data layout, the execution, more advanced things around hierarchical parallelism and other features. So what do we want in an ideal world? Well, we want to get the maximum possible performance out of our hardware on our application. We want to be able to run many different algorithms and express them intuitively, all within a single code base. You don't want to have to maintain multiple versions of your application, one for CUDA, one for CPU, one for AMD-based GPUs, and so on. So the one approach that people have tried is various parallel or domain-specific languages, which is very interesting as a sort of computer science research project, but such as Chapel, yes. But you need to have a compiler, you need to have all the libraries that you want to use, or else you're going to end up writing them in Chapel, perhaps. Rather than just being able to reuse someone else's work, you're going to need the tools to understand the performance and debug these things. So these things aren't really used very much in practice because people don't want to have to learn a new language. It's an investment in your time to, say, come on a course like this or go and buy an introduction to CUDA textbook and then work your way through it. So people generally stay away from these things. So you might say, well, what about CUDA? And that, because that is a parallel domain-specific language, the domain being programs that run on NVIDIA hardware. But this is tied to NVIDIA's hardware and software ecosystem, which is perhaps not for everyone. So if you want to write a real application, something that's more than just a single benchmarky kernel or a mini app that people like to do in this sort of space, you need to think about what you're going to do. So one thing you might do is maintain a number of implementations of the core kernels of your application. So you might find that 90% of your lines of code in your application are doing things like I/O and setting up your problem and passing inputs and doing domain decomposition or whatever other thing it is that don't actually have to run all that often. You just run them once at simulation startup or when you're doing I/O or so on. And you might decide, well, I'm just going to do multiple implementations of my kernels. And that's okay. It's an approach that people do use, but that's still duplicating your work. And these parts of your application are usually the ones that take the longest to write. You want to tune them to get good performance. Otherwise, why are you bothering to run on parallel hardware in the first place? So you might try a sort of a portability layer, like something like Intel's threaded building blocks or OpenACC, we've just been talking about, especially if you're in the Fortran world, that's perhaps that or Openmp target directives are perhaps the best solution. You could use OpenCL that Kevin talked to you about this morning, although that's somewhat hard work. You could use SYCL if you're a C++ application and you're willing to try that, or you could try something like Kokkos, which is what I'm going to talk about right now. So let's sort of think about a very simple loop. We want to take some array of data x, and we want to scale this in place by a constant. Let's call it a. So this is some very simple scaling of our array. So if we express this loop in the standard C programming idiom, we've got for some index variable equals 0 up to but not including the number of elements, and then we have the condition for moving to the next the statement to move to the next item in the loop body. And then we can split this up into multiple things. We can say that the pattern is a for, which means in this case do a thing across every a range of values. We have our execution policy, which explains to the compiler and the hardware how to run something, which is saying that we're going to just start strictly at the first element, and we are going to go run through all of them strictly increasing, and then we actually have our body where we do our combination. So actually performing a computation in this sort of data parallel approach is a combination of the pattern and the policy, which sort of steers the execution of our the real calculation. So let's think about Openmp, which I think it was around a third of you had some experience of. And so we have our pragma, which says we are going to parallelize this loop with Openmp, and we are doing a for loop. And we've got our pattern, which is sort of pulled out for us here, and the policy, which is this parallel part. We're saying we're going to run these elements in parallel, and that we're going to run from 0 up to the number of elements, increasing in a way. And the OpenMP compiler needs to understand and recognize this loop body and say, okay, that is a certain execution policy. And then we've got our body exactly as before. This is just the actual computation. And what this will do is this will distribute the iterations of the body across one or more threads for us, hopefully approximately as many as we have cores on our system. And the execution of these will be asynchronous, the threads being joined at the end once they're all finished. So let's show you a bit about Kokkos doing this. So Codecos is a purely C++ library, so any Fortran programmers, I'm afraid you are out of luck. C programmers, you're slightly less out of luck, but this is fundamentally a C++ library. Sorry, Mark, by that you mean...
I've dabbled C++ and C, actually. I'm not a novice, really.
Oh, okay. Yeah, so maybe that's a good question. So who's written at least one C++ program? If you could raise your hand. Okay, and who'd consider themselves a fairly strong C++ programmer? Keep your hand up if so. Okay, so a handful of you. Okay, well, we're not going to delve too deeply into C++ here. You can treat it for your purposes much like C. However, you're going to have to deal with the syntax for using templates a bit later. So what we're doing here in Codecos is, first of all, we're including the library's main header. And then we are saying that we want to run a parallel for loop with some policy on some body. And this is the Kokkos way of separating these things out, expressing a certain pattern, and we're saying the policy, which will be some object that we'll talk about in a minute, and the body again, which is something we'll talk about again. So actually the body is specified as what's called a function object, or a lambda, or a functor in C++, not the mathematical computer sciencey functor, unfortunately. So let's show a little bit more about this. So if we're going to use the same example of before, scaling a array of numbers by a constant, we need to create a function object. And here we're going to do it explicitly and by hand. So we're saying we have our scale structure. It has two members, one A, which is just the constant, and a pointer to the data as its other member. We then need to be able to construct one of these. So you can either do it, construct it with an explicit C++ constructor, or you could have just omitted that and had a sort of a purely trivial type that you would just go the instance dot A equals something and instance dot X equals something else. And then we have to provide an overload for the function call operator in C++, which in C++ is written in this way. So we're saying that if you take an object of this type and you treat it as if it were a function, we can give it one integer argument, which is going to be the index, and it's not going to return anything. And this const here means that it is not going to be modifying any of its data members. And then we include our code here. We're saying that x gets scaled up by a at the given index. So this functor just acts on a single element of the computation for us, and something else has to take care of arranging for this to be called in parallel across every element in the array. So here we need, as well as the body, which we can pass in this second argument, we need the policy, which says that the range is of the appropriate length. So Mark says, is that a style or required? So that's stylistic. So that's a common C++ idiom for indicating member variables. So let's create our data. We've got A as a constant. We'll just double every element. We're saying that X is a dynamically allocated array of doubles of size n elements. We create our scale function object, which we do by just declaring a variable in the usual style and saying that, passing the arguments to the constructor here, A and X. And then we call the Kokkos parallel for function call, the first argument just being n elements, which indicates a range starting from 0 and of the length given. And then we provide the instance of our function object there. So to make this code a little more convenient, you can use a lambda, which is just an anonymous function that you can declare anywhere in your code in C++. So as before, we've got A and X. But then when we have our function object, instead of instantiating, declaring a class and instantiating an instance of it, we simply put an inline lambda definition. So the square brackets are the thing that introduces a lambda. And you can have what's called a default capture specifier, which says to the compiler, an equal sign means take any variable I mention inside the body of this function and copy it as a member variable of this function object you're creating for me automatically. And then again, we have one argument, which is just an integer index, and then the body exactly as before. And this just refers to the variables that are in scope. So the compiler can see a use of X and know that that was a local variable and capture a reference to that there. And the same for A. And we can just stick our computation in. So this is now starting to look much more like a traditional for loop. Or if you've used the C++ algorithms library, like a stood for each. So let's think about a different product, something like the vector product between the scalar product between two vectors, so a dot b and so on. So if we were going to write this in a sort of a traditional procedural way, we've got our two arrays a and b. We set our result variable to 0, and then looping through the number of n elements, we multiply the two vectors element-wise, and we add that product to our accumulation variable result. So in OpenMP, we can transform this to use a reduction clause. So as in the first simple iteration example, we have a omp pragma parallel 4, but we also need to add a reduction clause. We need to specify the operator to use, which is a plus, and the variable over which that reduction is occurring. And so we again iterate over the range, and we just go, the result is equal to some contribution from that run of the loop. And the OpenMP runtime will take care of reducing the answers from the threads using the plus operator that was specified here. And so we have to separate out what the pattern and the policy and the body are. So the pattern is the pragma 4 reduction. And the policy is that we're doing it in parallel over some range of index space. So Codecos again has a similarly named thing. It's got a parallel reduce pattern. We start off saying our result is nothing, is a 0, and then we call the Codecos parallel reduce function with some arguments. The execution policy is just as before. We just pass in an integer specifying the number of elements. And then we need to have our body of the loop. So this body is a little different from the previous one. We don't just accept the index of the item we're working on here. We have to also accept the current value of the accumulation variable in some thread context that we don't need to worry about. And we have to accept that by reference here. So if you're not a C++ programmer, this might be a little confusing. The ampersand simply means pass the argument by reference, not by pointer. The syntax for accessing it is exactly as if you'd passed it by value. However, the that named variable sum, the parameter, doesn't actually own the data. The variable that's being pointed to it is provided by the caller of this function. So within the loop, we do our contribution to that sum, just as before. We say A at the index times B, the index gets added onto the accumulation variable, as before. And then the final argument to the parallel reduction is the variable where you want to store the result. So a few things is worth noting. The sum variable is kind of thread private in OpenMP speak. Kokkos manages what value gets passed in to every run of the loop body for you. So you don't need to worry about that. In practice, if you were to say run it on 10 threads on your CPU, Kokkos would take care of starting up 10 copies of that, probably starting from the initial value of result, and then at the end it would make a few extra calls to the function body to combine them together, because nowhere have we said explicitly to Kokkos that this is a sum. Okay, the sumness is included here because Kokkos has a function that will do the work for you. It has, hold on, no, it's just the default. Sorry, I'm confusing myself. So what we want to do now is have stopped talking about you, because what the next part of the talk is to talk about how Codecos deals with abstracting the multiple memory spaces and execution spaces away somewhat, so you don't have to deal with them constantly. What I'd like to do is have a crack at the first exercise for Kokkos. So one thing that you'll need to do is, because I'm afraid I had forgotten to update these to use the new architecture of Cirrus, after the new software after Cirrus got upgraded a few months ago. So I only did that yesterday morning while Kevin was speaking. So you'll need to do a git pull on your repository on Cirrus in order to get the latest version. I will stop sharing this and share my terminal instead. If you go to the GPU course, you could just do a git pull to update from there. And if you, for example, wanted to double check, if you look at the log, you'll see there's a commit from myself saying update the Kokkos exercises. So if you could make sure you've got that before you try and use Kokkos. The other thing you will need to do is you'll need to use the extra modules. Sorry,
I just need this. Sorry.
Okay. Sorry, getting a view of baby Fergus there. We provided the Kokkos modules just for this course. They're not globally installed on Cirrus, so you'll need to get them. Is there a at typing? You need to module use this path, and I'll just paste that into the chat for you. And then you'll be able to module load Kokkos and have access to this nice and easily. So to use it just on the CPU, you can just go module, after you've used that module path, you can just module load GCC and Kokkos. And then you should be able to do the first exercise, which lives in exercises Kokkos #1. Yes. And to compile it, you should just be able to type make and then run it with the submit script on a GPU, on one of the backend nodes. This one doesn't actually need GPUs. We'll talk about that shortly once had a go at this. Yeah, so give you until about 3 o'clock to have a go at this, and then we'll have a little break. But you need to load Kokkos and GCC. Okay, so according to the schedule, it's now time to have a quick break. I'm just going to go and get a cup of tea, and I'll be back shortly. Aim to talk about Kokkos and memory management again at about 10 past, but obviously happy to take questions about this first step at that point as well. So I'll be back shortly. Okay, so yeah, so as I alluded to before, you need to do something a bit different to deal with the separated memory spaces that you have when you're dealing with a GPU. So we'll talk about the way Kokkos abstracts this. So Kokkos provides a lightweight class which represents an n-dimensional array, and it calls this a view. So, for example, the first line of code here declares a variable called x that is a Kokkos view of type pointer to double. And if you're a C programmer, you'll be fairly happy with the fact that pointers to double are the same as, in some sense, an array of doubles. And here we give it a name. We're just calling it my vector, and we're saying the size of it. And this will be a dynamically allocated array of doubles, the number being given at runtime, n elements. And then in our parallel for, we can run over n elements, and inside one body this, we can say that x at an index is scaled up by a constant again, exactly as before. So the only difference in this code inside the function body is that instead of using square brackets like a C or C++ programmer would naturally use for indexing, for element access, subscripting, whatever you want to call it, we're using round parentheses for function call. And the reason for this is basically because C++ doesn't let you have multiple arguments inside a subscript. They might change that in C++ 23, but it's still only 2020. People have to argue about this for a long time to make changes. So instead we use round parentheses for element access here, which will make Fortran programmers happy. So the data that sort of backs this view and that's associated with it is in what Kokkos calls the default memory space. So what's a memory space? This is, given we've been talking about the architecture of these things, talking about separated CPU and GPU memory address spaces, hopefully this will be a fairly obvious thing for you. It's basically where does the memory live? And the Kokkos allows you to have a default one of these that is controlled as part of, it's controlled at compile time. So when you set these things, you can say that for the Openmp device, the default will live on the CPU. And as well as using the default one, you can control this explicitly in your code via a template argument. So you can say, I'm going to create a Kokkos view of a one-dimensional array of doubles in the CUDA memory space. So you just pass that as an argument to your to the template parameter list, and then otherwise treat it exactly as before. So when you have your views which live in some memory space which is not necessarily the one that's accessible on the host, you might want to have an easy way to get at that data. And so let's create a type def or a type alias for the vector type. So instead of having to type the rather long Kokkos view of double pointer, we'll just say that's our view vector type. Then we can define one of these vectors in the default space. And then from that, we can construct a host mirror type. So we can create a mirror view of a view, and that will give us this host mirror type, which we're calling h_x. So we can initialize this here. We're just setting every element for one. And then when we want to copy from the host to the device, we just call this Kokkos deep copy. And this is sort of part of the philosophy of Kokkos. They won't let you do expensive things by accident. So if you want to move data, which is a potentially expensive operation, you have to ask for it. So it's saying you deep copy 2x from hx. The way to remember the ordering is, remember, it's just like assignment. The destination goes on the left-hand side. So as well as a memory space, Kokkos has the concept of an execution space. And a memory space has an associated default execution space. So, for example, we can say that we want to create a range, an execution policy to go over some range in the host space here. And we say we want to go from 0, start at 0, going up to but not including in elements. And I think in actual fact, you don't have to include the 0. It will, if you omit the first argument, it will implicitly start from 0. And then when we call our parallel for or our parallel reduce, whatever, we give this policy object as the first argument. And Kokkos will know from the type information encoded on this variable that it needs to run it in the host execution space. And so we can access the host view, hx, that we declared on the previous slide at an index, and we can scale it up by a, just as before. So data layout. So yesterday we talked about how to lay out your data for the best performance, for example, with memory coalescing on your GPUs, and saying that this is basically transposed from the way you might naturally do it if you're a C++ programmer. So let's think about something a little more complex than the scaling a vector by a number thing. So let's do an inner product of x and y, which are vectors, across a matrix. So this is matrix A multiplies by x, giving you a vector, and then we take the dot product of that vector with y. So the dimensions, it doesn't have to be a square matrix, so let's have an m by n matrix, and x is going to have size n and y will have size m for mother. So to compute this dot product, we might, in sort of a procedural way, just say the result starts at 0, and then we're going to loop over I, going up to m first, set our row-wise sum to 0, accumulate, then loop over the columns, adding our contribution to that, and then we're going to say the final, this row's contribution to the result is the relevant element of y times that, times the element of our temporary vector, if you want to think of it that way, ax. So there's a nice little diagram of the sort of row and column major views of this. So I always struggle to think about which one is row major and which one is column major. I always try and think purely in terms of left fastest, right fastest, because there's no natural to me ordering of I and j onto x and y in this. But for example, if you have a row major data layout, as if you have your data laid out this, the arrows sort of indicate as you move one element forwards in the flat view of your data, this is how you move through the two-dimensional array. So we go along that way, along that way, along that way, and so on. Whereas if it's column major, it's the transpose of that. We start there and we go down the columns, go down the next column, and so on. So Kokkos lets us control this with these layout types. So every view has a layout associated with it, and here we are explicitly setting that. So we're saying that we're going to have a Kokkos layout right, so that means the right varies fastest, the standard C way of ordering data in a multi-dimensional array. We're making a type alias layout for that, and we're going to create our view, a two-dimensional array of doubles here, A, and then two one-dimensional arrays, X and Y, with differing numbers of elements. And then we can do our parallel reduce. We can loop over all the M's, doing our, I'm having my doubts whether this is column or row work now.
Is cycling faster, so it is your C-style memory storage.
Yes, so, yeah, so I mean it's layout right, yeah. So my problem is that I never know which one, left or right, from my rows and columns.
M is rows, isn't it?
M is rows.
So you're
yes, probably
decomposing across the rows.
Yeah. So each row gets done in parallel, and each execution of this runs one dot product of a vector, a sub part of your matrix with the input x, and creates its local sum, and then we use the reduction variable. We increment that by our local contribution, and then we get the result we want at the end. But is this the right layout in some sense? So, well, it depends where you're running it. So every execution space has an associated default layout, which, for example, with the CPU's layout right is going to be the faster one. It will let your CPU caching do its work to the best, whereas on the GPU it will use a layout left, and this will mean that you get the best memory coalescing when you have multiple blocks of threads running together. And choosing the right layout is very important to get good performance. So another feature that Kokkos has is hierarchical parallelism. So in the example reduction we had there, we've got this parallelism only over the rows of the matrix here. So the sum over n runs on one thread. So in one thread, we're computing all of those things. And I think the first thing we talked about in the optimization lecture yesterday was you need to have as many threads as you possibly can, as much parallelism as you can to get good performance from a GPU. So we need a way to express that. So Kokkos has a sort of a teams policy. So we'll just make a little alias, a type alias, to reduce our typing. So we've got the Kokkos team policy member type, just alias there. So we're going to create a policy in the default execution space. We don't need to give the template any explicit arguments. There are sensible defaults, but we do need to instantiate the template. So that's why there's the empty angle brackets for template instantiation. We're saying the variable's called team policy, and we say the number of teams and the team size. So talk about what sensible numbers for that might be in a bit. So then we do our parallel reduction as before, using this team policy as our way of working, and then we use the type alias member type here to pass in, and this is saying this is in some sense represents my team of threads of execution which are going to do that whole row. And we have our reduction variable exactly as before. So every thread in this team is active, and they can potentially share memory. So we can get the sort of the team's number, or the league, the rank of your team in the league, and then you've got the individual team members' rank within its team. And so we need parallelism, or some sort of reduction over the columns, and then compute a contribution to the output reduction variable, our sum. So we need to nest our parallelism here. So we can say to Kokkos, we've got our team execution policy, we need to do it over m things, and we don't really care what the team size is, so we can tell Kokkos, please figure it out for us. Please choose something that will perform reasonably well via whatever means, whatever heuristics that someone else has figured out, which is always nice. So we pass the team policy into our parallel reduce. Got these parts we just talked about. Got our local sum 0. We get our team's rank within the league. So this is basically the row of the matrix that we're working on. We create a team thread range, which is another type that Kokkos provides us, saying, given the member I'm working on, iterate over all the columns for me, please, all n of them. And then we, inside the parallel reduce, we call another parallel reduce to work across that using this other thread policy object. And here we're doing index j. We've got our column sum here. We add a single element's contributions to the column sum on, so it's aij times xj, and then that gets returned into the sum local variable. And then we need to be careful. We need to make sure that we only do this once per team. So we need to get on the sort of the 0th member of our team. We add a contribution to the top level reduction variable, the row sum, and that should work for us there. And you can take this a step further if you are wanting to really get the best you can. You can have your sort of team thread level code, your thread level code, and then vector instruction level code if you want to go for that. I don't want to talk too much about this, so I'll just refer you to the Kokkos documentation to do that. I just want to make sure you know that that's a possibility. So, a bit of a summary. So we need to identify the sort of fundamental parallel pattern that we're wanting to perform. So a for loop, a reduction. We haven't talked about scans, but that's the sort of, it's much like a reduction, but you get a partial answer for every element through your iteration. There's also some task graph things that Codecos makes available. We can control the memory space and the execution space of our code. We've got the host space, the CUDA space, and we've also got the CUDA unified virtual memory space, and shown you the types that Kokkos uses to control the memory layout, and sort of done a simple introduction to the way you can do the more complex execution configuration via these sort of range policies and teams policies. There are also execution policies that Kokkos has around n-dimensional loops. So, for example, if you were doing an image processing type example that we did yesterday or earlier today, you might want an n-dimensional range thing. Kokkos also has classes that will let you do tiled loops, and you can create your own of these if you have the need to and like programming with templates in C++. So Kokkos has a bunch of other features that help with debugging and profiling. So it's got hooks for Intel's and NVIDIA's profiling tools. And there's also some stuff to help incrementally moving an existing code base over to the Kokkos way of doing things, for example, with the dual view and the memory coherency stuff. So there's also AMD ROCm support. So yes, you can tell these slides haven't been updated for a while. I have not checked whether they've got they're happy with the support they have for ROCm. No doubt the Kokkos GitHub page will say what the state of that is, unless Kevin knows offhand.
Don't know offhand. If anybody can get their hands on an AMD GPU, good luck.
Yes, I would dearly like to have a go, but you can't seem to get them for any money these days. So yeah, so if you would like to just carry on with the Kokkos exercises, there are 4 in total in the repository that should show you some of the basics of how to use this. Kevin and I will be online until what time? Until about 4 o'clock. But I could stay on about another 15 minutes after that, I guess. And happy to take questions about anything on the course. Kevin, do you want to say anything now about the Thursday and the bring your own code hackathon thing?
I can do.
Or do you want to wait till the end?
We may as well try now. So, by the way, that Kokkos stuff is quite complex, so don't be too alarmed if it does look so. But it hopefully gives you a feel for the kind of things that people are doing to try and abstract the problem of getting portable performance. So you're surely welcome to come back again on Thursday if you want to continue with the exercises, having digested the material a little. But as I said on Monday morning, we will start. Actually, I think if Rupert, if you move forward one slide, yeah, we.
Oh, of course, we have Alan's.
We're scheduled to start at 10 with a guest lecture from Alan Gray at NVIDIA, who will say something about CUDA 11, the latest release of CUDA. And then you are free to go on with the exercises, or you could try to bring your own code and we can try to help you. Or if neither of those apply, we have a little mini app that perhaps you may want to have a go at for some practice, perhaps in the programming model of your choice. But there will be more about that on Thursday if you're interested.